All right. Hello, everyone. We are now just past the hour, and we are hopefully live streaming on YouTube right now. So everyone can hear me, I think, yes. I'm getting some thumbs up. So I just wanted to say, first of all, hello, and welcome, everyone. Good morning, good afternoon, good evening, wherever you are, and a warm welcome to the February 2025 edition of the Rocky Worlds discussion. So my name is Limbold Christmas, and I will be the moderator for today's session, where we were going to be hearing from Michael Way, who will be presenting his talk on Venus's climate, history, and connections to recent spacecraft data. And just before I hand over, I just wanted to say a couple of notes on netiquette. I know you guys have probably used Zoom before, but we ask that you ideally will be using your full name on your Zoom account, and that you save your questions for after the talk, at which point you may raise your hand using the raise hand button, and I will call on you and ask that you unmute. Ideally, you'll have your camera turned on because it's nice to see you. And if you're not able to do that, to just write your questions in the chat, either on Zoom or on YouTube if you're watching on there. And I will read those questions out for you. So with that being said, I'm very happy to hand over to you, Michael. Thank you very much.
Okay, great. Just need you to stop sharing. Let's see here. Okay. Yes. Now, hopefully you all can see that.
Yeah, it looks great.
Okay, great. Okay, so as Lynn graciously said, this is a small talk about a possible climate history of Venus in connections to recent, and I should say, future spacecraft data. Of course, such a long title wasn't really feasible, I thought, so I left off the future part. But you'll see a few future missions that we're going to be sending to Venus in the next decade or so in my talk. So let's start out with the obvious. The idea, as I say here, of a habitable Venus has been around for decades. But how could Venus ever really be habitable when you have these strange numbers that we can see here? If we look at the insolation that Venus was receiving 4.2 billion years ago, for example, it was 1900 watts per meter squared. That's 1.4 times what Earth receives today. And we already know Earth is at the edge of the habitable zone. And of course, today it's receiving almost twice as much as we receive today. But let's look at some different theories for Venus's climate history that have been discussed over the past few decades. So there's a couple of views of Venus. I'm going to talk about the two traditional views first. This is the first traditional view, and I would say that it's the null hypothesis. So the idea that Venus has never been habitable and has always basically been a hothouse world from the beginning. And in this scenario, Venus had a long-lived magma ocean of order 100 million years or less. We can argue about that time scale. All of its primordial water, which was in the atmosphere at this time, was lost, mostly through H2O photodissociation. The H2O easily escapes to space in this period of time, and the oxygen that's left over from the photodissociation is absorbed by the magma ocean. We've been bone dry for about 4+ gigayears. No ocean condensation is possible. And the high D to H ratio that we measure of about 150 times that of Earth from the Pioneer Venus probe, which I'll come back to later, is from this epoch. And this is supported by a number of works, Ingersoll all the way back in 1969, Hamano and Lebrun both in 2013, and more recently by Turbet in 2021. Although I should mention that the Hamano and Lebrun paper don't make a conclusive argument for or against this. They provide two different scenarios. The second traditional view has been that there was a short-lived magma ocean period, something similar to what Earth probably had. The steam atmosphere condenses out on the surface, and voila, you have oceans. You have something around a 1 gigayear habitable phase. The sun's luminosity continues to increase through time. As you may know, 4.5 billion years ago, the sun's luminosity was about 25% what it is today. But as we go through time, that ramps up to the present day, and we go from a clement state to a moist and then a runaway greenhouse. And the high D to H ratio is from this epoch. We transform into the present day Hell House world in the end. And this is supported by work that goes all the way back to Pollock in 1971, Bullock and Grinspoon in the 1990s. And again, those Hamano and Lebrun papers from 2013 who couldn't decide which side of the fence they were on from their models. So what are the things about these two traditional views that are interesting and tell us something about who's right or who's wrong? Well, the traditional view one explains the present day state pretty well. As I said, the H2 from the steam ocean atmosphere phase escapes to space. O2 is absorbed in the magma ocean. We never had any volatile cycling as we've had on Earth for almost 4.5 billion years. The only question that remains is why it still has a thick atmosphere. Depending on whether you believe that magnetic fields play any role in atmospheric escape or not, I think that that's up for a large debate these days, since the atmospheric escape rates for Venus, Earth, and Mars are almost exactly the same. The problem with the habitable view is that it doesn't completely explain the present day state very well. The big question is, where is the oxygen? There's tens to hundreds to thousands of bars of O2 missing in this scenario. And there's been work by Luger and Barnes, Worth and Pierre-Humbert, Vicky Meadows and her team, that shows this is exactly what would happen, that if you go from a habitable state to an uninhabitable state, you go from a moist to a runaway greenhouse, that you end up with tremendous amounts of oxygen left over in the atmosphere. Because it's easy to lose your H2, it's much more challenging to lose the oxygen. But was there a steam atmosphere? That is the question that we're debating now with a lot of recent work in the community, which I'm really encouraged by seeing. This is a nice figure, or part of a figure, from a paper from 2022 by Dan Bauer. And of course, there's been more recent work by Nichols and Lichtenberg and company. I would think one problem we have with understanding these modeling efforts that we've seen for the most part so far is that we really don't have good compositional constraints on what these magma ocean atmospheres consisted of. And as you can see here, if you just look at the 30% melt column here, we have atmospheres that depend upon the redox state. Here's the iron Woodstock buffer at 0.5, oxidizing and reducing. We have atmospheres that are, for example, CO dominated with CH4 and some H2, others that are CO2 dominated in an oxidizing environment. Here we got CO, CH4 again, and all these different kinds of atmospheres. And these atmospheres are hundreds or over 1,000 bars in their atmospheric pressures. These are very challenging atmospheres to model. And that's why so far there's only been one 3D version of these ever modeled, and that was by Martin Turbay and his team. The rest have been 1D models. And as Martin showed in his model, you really need a 3D model, at least to understand what the clouds are doing, which can play a really important role in radiative balance of the atmosphere. So what else do these works tell us? One thing that I think is overlooked a bit is that water is highly soluble in most of these melt scenarios. For example, Paulo Sossi has a paper from 2023 showing solubility of water in periodite liquids and prevalence of steam atmospheres on rocky planets. That's a really nice title. And he says here that because of this, the steam atmospheres are rare. And we tend to see that in more recent work as well. For example, this plot on the right comes from a more recent paper by Maurice et al. In 2024. But again, we don't have good constraints on what the post-accretion atmospheres of Venus or even Earth were at this time period. We still have a lot of work to do to better understand that. Okay, let's move over to a bit of a newer view that I want to discuss with you. So in this newer view, again, we assume, like we did in the second traditional view, that we have a short-lived magma ocean or late water delivery. We have a relatively long period of habitability, which is undefined, anywhere from 1 to 3 gigayears. And there'll be a transition from this temperate to hothouse state, which we have very poor constraints on how that would actually go about. And it would not be due to the insolation of the sun increasing through time, as you'll see. And this goes back to a lot of work, some of which I've already mentioned a bit: Grinspoon and Bullock in 2003, Abe 2011, LeConte, Yang 2014, which I'll talk about in 2 papers from my own group. Not so many fellow travelers here. So the real question we have is there evidence for surface liquid water in Venus, in Venus's history? And if yes, then we believe that clouds in concert with rotation rate may have played a key role in Venus's ancient climate. So what is the traditional evidence for liquid water on Venus? Well, there's a couple lines of evidence, none of it conclusive. The first is the PV, as I call it, Pioneer Venus, high D to H ratio, about 150 times Earth's D to H. But in this case, the loss of the water And the type of loss and the timescale of that loss is completely unknown with the constraints we have today. There's a paper from Watson in 2007 who believes that the 40 argon numbers from the Pioneer Venus mission point to hydration of the crust, which would indicate that there was liquid water on the surface. There's the Galileo NIMS mission. So Galileo was a probe, as you may know, that went to Jupiter, but on its way to Jupiter did a Venus flyby to get a gravity boost. And there's some evidence that in the highlands, like in Ishtartera and places like that, that they might be felsic rocks or maybe even granitic, which requires water to form those rocks. There's a couple papers based on the Venera 8 data from Nikolaevna and Shelnut, already recently in 2019, who did a reanalysis that believe one of the rocks found was a greenstone belt, which also requires some kind of water processes. There's a more recent paper by Richard Ernst's group, one of his PhD students, Kwaja, from 2020, that look at the morphological features on the surface of Venus and believe they see evidence for fluvial erosion in the tesserae in the highlands regions. I would say that's a bit controversial, but nonetheless, that's the evidence that they put forward. Are we going to be able to resolve this? I think so in the future. Between the Da Vinci mission, which is coming out of Goddard Space Flight Center, Veritas, which is coming out of JPL, and Envision, which is an ESA mission, all three going to Venus in the next 10 years, we should be able to resolve some of these questions we still have. Okay, so let's move on to clouds and rotation rate and how those play a role in maybe stabilizing early Venus's climate. So the climatic importance of clouds, as I say here, or how to keep your world habitable. This goes back to a figure from Jim Pollock in 1971 in Icarus. Here he uses a 1D climate model. A non-grade calculation of the runaway greenhouse impacts for Venus's past and present. And I think this figure is really interesting because what do we see here are some estimates of what the incident solar flux is on the left for his 1D climate simulation and his surface temperature for each of those simulations. And what you can see, for example, if you look at Venus 4.5 gigayears ago here, when it was receiving, as I showed you in my second slide, 1900 watts per meter squared, he gets a global mean surface temperature in his 1D model of about 290 K. He does that by using 100% cloud cover. He never really explains why he tries 100% cloud cover, but he does put it in the paper. He mentions there's another plot in the paper where he does a 50% cloud cover, and all of those simulations go into a runaway state. And as we know today, Earth has about 68% cloud cover on average. Okay, so we're left with this kind of quandary. 100% cloud cover works, but how do you make it happen? Well, we had to wait 43 years, and we had to get the exoplanet community doing modeling to tell us. And that comes back to a paper from Jun Yang and his collaborators at University of Chicago in 2014 in this nice AppJ letter paper, Strong Dependence of the Inner Edge of the Habitable Zone on Planetary Rotation Rate. Sorry, these plots look a little complicated, but they're not that complicated. Each one of these lines, let's look at the plot on the left here, represents a series of model runs. Each dot is a model run with a 3D GCM, the NCAR GCM, CAM3. And what we can see here is that this line, the black line, is for modern Earth day length of day. The red line is a length of day increased by 16 times, so rotating more slowly, then 64, then 128, and 256. These light gray lines are the insolation that early Venus would receive 4.5 billion years ago, that 1900 watts per meter squared. And this other gray line is modern day Venus. And of course, 1361 is present day Earth. And what you see as he ramps up the insolation for the modern Earth rotation rate, he rapidly goes basically into the moist greenhouse, and in theory, into a runaway greenhouse. Of course, we don't know because these models cannot do a proper runaway greenhouse, but the models become unstable and basically we cannot go past there. And you can see that maintains more or less the same structure from 1 to 16 days in length. But as we get to 64, 128, and 256, we can see the global mean temperatures. As we increase the insolation on that x-axis, the global temperatures don't climb as quickly, and we're able to go quite far in insolation to quite high values and still maintain global temperatures below about 310, as you can see here in the Kelvin. In the right plot, you can see that that is basically due because of increases to the planetary albedo. So you can see on the lower left in this plot on the right that for 1 in 16 days, your planetary albedos don't get very high. But for the 128 and 256 days, you can see the planetary albedos increase extremely high, even at these very high insolations. So there are ways to get the equivalent of what Pollack would call 100% cloud cover just through slow rotation rate. So why is that? It's basically because the Hadley cells are different from Earth's on these slowly rotating bodies. And it's basically the difference between a strong versus weak Coriolis force. So on our planet, of course, we have 3 Hadley cells, 3 in the north, 3 in the south, and those determine the direction of the trade winds, of course, and climate zones on Earth. Whereas on a slowly rotating body, here's an idealized picture on the right, you can see there's 1 Hadley cell in the north and 1 Hadley cell in the south. And that's because the Coriolis force here, the Coriolis effect, is very weak in a slowly rotating body. And what is the result of that is what you can see on the left here again is the rapidly rotating. This is from the Yang Piper in 2014, one of his GCM simulations, where you can see this banded type structure. But on the right, in the 128-day case, you can see this very substellar cloud deck, very large substellar cloud deck, which is blocking out most of that sunlight with these very high albedos, and hence that 100% cloud cover from Pollack. So it is possible to get 100% cloud cover in these slowly rotating models. Now, I would just say as a caveat, these are just models, and they could be wrong. I would say so far, we know of at least 4 different GCMs that have been able to produce these. But I always like to say, as very common, all models are wrong, some models are useful. And we'll find out when we actually get some data on hopefully similar type worlds around nearby stars, whether or not this effect exists or not. Okay, so the next question we have is, what was early Venus's rotation rate? And was it rotating slowly enough for these cloud effects to take place? I could give a whole talk on this. It's a really interesting topic. A lot of work has been done over the last 40, 50 years on this topic. So I don't have time to go into them. But I just want to say there are many ways to make Venus a slow or retrograde rotator with a small obliquity. Through things that we're all very commonly familiar with, things like impactors, of course, large or small, solid body tidal dissipation with the sun, core mantle friction. This is work that's been done by Laskar and Dobrovolskis and collaborators, atmospheric tides, and even if it had oceans in its early history, ocean tidal dissipation, the work that I've done with Matthias Green and collaborators. So there are many ways to make this happen. So if we assume that Venus was a slow rotator for much of its history, let's test this habitability assumption above, and we'll use the Rocky 3D climate model, which my group develops in New York City. So this model, of course, has one of these horrifically long and complicated names, which I'm not going to go through, but you can read it yourself. This is version 1 of the model, and this is developed at the NASA Goddard Institute for Space Studies. We're the child of a parent Earth climate model called Model E, which takes part in IPCC, CMIP, and PLIOMIP. And we remain tied mostly to our Earth climate model. So every time the Earth climate model releases a major revision, we take that revision, we add our extensions to that revision, and we march on forward. They have a lot more money and a lot more horsepower than we do. So we have to take advantage of them. That's unique from many other groups, by the way. Many other groups have broken off from the parent climate models and march forward from there. Okay, so this model is what I think is termed a full complexity climate model. This is a model with an atmosphere with 40 layers. We tend to run this model as a dynamic ocean with 13 layers, not a slab ocean, which is typical in the exoplanet community. We have a land surface with 6 layers. We run it at fairly modest resolution, 4 by 5 degrees or 46 by 72 in grid cell numbers. And we use a highly flexible third-party radiative transfer scheme that is known, I suspect, to many people on this call, called Socrates, is developed at the UK Met Office and Exeter. The reason that we're running Socrates is the native GISS radiative transfer scheme, while very fast and very efficient for modern Earth, will not work for larger insulations or different atmospheric compositions. So we had to find a different way. And we had a postdoc many years ago who worked at Exeter and with UK Met Office named David Amundsen, who coupled this radiative transfer scheme into our model about 10 years ago. Okay, so in the simulations, I'm going to show you a few results of very quickly. We have 5 different scenarios. One is an arid Venus or a dune world for those of you that are sci-fi fans. Take your favorite desert world, where we put 20 centimeters of water in the soil only. This kind of amount of water could even be consistent with a late veneer, even if you started out dry. The second scenario is we put 10 meters of water, global equivalent layer, in lakes. So in these first three scenarios I'm going to discuss, we take modern Venus topography and we use that. So again, in the lowest topographic regions, we fill up the planet with this 10-meter GEL. And again, this would be consistent with a late veneer type delivery. Then we have a much more Earth-like planet where we put three 10-meter GEL in lakes and in oceans that would require primordial amounts of water. And then we do the typical 158-meter deep aquaplanet. Again, these are fully coupled oceans with no land, and a 310-meter modern Earth with bathtub ocean, as we call it. So we don't model the full depth of the Earth's oceans, mostly because it takes a long time for the model to come into equilibrium. I'm mostly interested in climatology. Okay, so this is a summary of those simulations. The ones that are kind of spaced here in distance are all overlapping, but I wanted you to be able to see each of the simulations. I'm just going to talk about a few of these. We did a few simulations with those shorter length of days, so 16 days at 4.5 gigayears, with a 1 bar CO2 dominated atmosphere, because there are some ideas that the very early atmospheres for Earth and possibly Venus would have been CO2 dominated, and you can see the temperatures are quite high for each of those 4 or 5 different scenarios I talked about earlier. Then we did another set of runs at 4.5 gigayears at 64, and then a set at 243 day length, which is what the modern day rotation rate is. And you can see exactly as you would expect from what I talked about in the beginning of the talk, that as we lengthen the day length, the surface temperatures drop on average. Then we've moved to 2.9 gigayears ago. Here's another suite of simulations that we've done. One with a 1 bar atmosphere at minus 243 rotation rate. So this is, again, using modern day Venus's rotation rate. And another suite of simulations where we used a 0.25 bar into dominated atmosphere. So these are 1 bar with 400 ppm CO2 and 1 ppm CH4. Otherwise, there's no oxygen in these atmospheres. Not that it matters so much, because oxygen is not a strongly radiative gas. The reason we pick a lower atmospheric density is there has been some evidence from fossil raindrop imprints on Earth from the Archean and lava vesicle flows by work by Sanjoy Sam and David Catley and collaborators that show Earth could have had much lower pressures in parts of the Archean. So I thought it was worthwhile to run a few simulations there. And it's exactly what you expect, that if you lower the atmospheric pressure, of course, your mean global surface temperature drops a bit. And then we did another suite of simulations here about 700 million years ago for Venus. And you can see the temperature goes up a little bit, but not as much as you would expect. Remember in the traditional view, I told you about traditional view number 2, the idea was that you had this habitable phase at some point in Venus's history, and it was the increasing solar luminosity that drove the planet to a runaway greenhouse. But my point here is that if you're in a slowly rotating mode and you stay in that slowly rotating mode, it's very efficient at keeping the planet cool because of that high albedo, even through increasing solar luminosity through time. It's very hard to drive the planet into a moist or a runaway greenhouse state. So we do not believe that an increasing solar luminosity through time is what's going to drive the planet into a runaway state, at least if you believe these models. And we even did one model run here where we used modern just to show that even at modern installations, as you saw in the Yang paper, are possible with the same sort of model. Then we take all of these points, and I'm going to distill them all into just a few points to make things look a little bit simpler. This is a plot from our 2020 paper in JGR Planets. And each one of these data points is an average of the minus 243 day simulation. So again, this assumes that Venus has had the same rotation rate today as it has had in the past. Where we have this Magma Ocean period, something we call a cool early Venus period. We stole this from the Earth literature. There was this idea of a cool early Earth phase before the late heaven bombardment sort of fell out of favor. And we borrowed that. So that this is before the late heaven bombardment really fell out of favor, I would say. And then we have a period of time where we have this temperate period with surface liquid water. The planet goes from a CO2 dominated type atmosphere into an N2 dominated atmosphere. An evolutionary path we think was probably similar for Earth. And then it marches on forward through time until something strange happens and the planet moves into a completely different state. Now, we don't know if this is exactly what happened. This period of time for the temperate state could have happened a billion years ago. It could have happened 3 billion years ago. We don't have any constraints on this temperate period, unfortunately. Okay. So, as I've shown you, some models show that Venus could have had a temperate climate and been habitable as we understand it, but at least 3 questions remain. As I've just shown you, how long might it have been habitable? That really depends upon the longevity of volatile cycling. And B, water loss. How long was the water around? And that's something the Da Vinci mission, as I mentioned before, that's coming out of Goddard Space Flight Center, will give us good constraints on. The second question we have is, what caused the great climate transition? I want to go back for one quick step for a moment. So back to the longevity of volatile cycling. I just want to remind everybody here that even though Earth did not have subductive plate tectonics 4 billion years ago, I don't think there's any argument about that. As we understand plate tectonics today, Earth certainly had volatile cycling for the last 4 billion years, because we do not have strong evidence for the planet being in an ice house or a hothouse state throughout the Archean, in essence. So we've had volatile cycling on this planet for 4 billion years, even though we believe we have gone through different tectonic modes in that time. So if Venus had a climate period in its early history, the longevity of volatile cycling would play a key role, and it would be likely to have it just from our own planet. Okay, the second question we have is, what caused this great climate transition from temperate to hot house? So as I've explained to you, we do not believe that this could have occurred through increases in solar insolation. And we propose in our paper that it could have been volcanism. And that volcanism could have happened through overlapping large igneous provinces. Probably the largest igneous province on Earth today are something called the Siberian traps. Okay, so what are these Siberian traps? Well, actually here is a picture of the Deccan traps. This is in India. These are volcanic edifices. This is caused from intrusive volcanism. I would just point out that although asteroids get a lot of press about killing the dinosaurs and extinction events, it's volcanism throughout Earth's history that has caused most mass extinction events. And the Siberian traps come from a period of time called the End Permian, which was the greatest mass extinction event documented in Earth's history, where 90% of all life on land and about 80% of all life in the oceans went extinct. So we think this is the mechanism for driving a planet from a temperate to a runaway greenhouse state. And so I wrote a paper with a couple colleagues of mine a couple years ago. One is Richard Ernst, who's an expert on documenting large igneous provinces, and Jeffrey Scargill, who's an expert in time series analysis. Probably Jeff is one of the best time series analysis experts in the world. And what we showed, looking at Earth's history of large igneous provinces through time, we wanted to see what were the chances of 2 Siberian trap type events or 3 Siberian trap type events go off at the same time throughout Earth's history. So we did a series of Monte Carlo runs. And what you can see here, I'm not going to go through all the details because, again, we don't have so much time, that throughout Earth's history, there was a 30% chance for a pair of the Siberian traps to go off at the same time and a 15% chance for a triple. Then the question is that what could override the temperate state? And that's research that's undergoing at the moment. So we'll find out. But we think it's a possible hypothesis for driving a planet out of a temperate state. Okay. Then the question is, if it was large igneous provinces, can we find the remains in the Veritas and Envision images? And what are these images? So Veritas and Envision will be doing high resolution radar maps of the surface. So the only really good radar resolution maps we have are from the Magellan mission in the 80s. Veritas and Envision are going to go back with much better instrumentation and much higher resolution. We might be able to discern if these things were there. And as well, the Da Vinci mission is going to have an actual optical camera. And as it floats down to the surface, as it goes through the atmosphere, it will actually we'll be able to tie what we see on the surface, at least over one of the highland regions, to what we see from orbit. That's going to be very powerful for understanding the surface of Venus. Okay, so the third question is, where is this ocean remnant oxygen? As I mentioned, it's very hard to get rid of this oxygen, right? We photodissociate the water, hydrogen escapes into space, and the oxygen has to combine with something else. And we don't see it in the modern day Venus. That is really the big problem with having a habitable period on Venus. There's no oxygen in the atmosphere to speak of today. So what about loss to space? I think the definitive work goes back to 2020 by a paper by a colleague of mine, Moa Persson, and that Venus could have only lost about 30 centimeters of water in 4 gigayears by atmospheric escape of O+. The point here is that ion escape alone cannot remove a large inventory, and you have got to remove the oxygen by other means. It's very difficult to move large amounts of water through atmospheric escape. Of course, her model assumes that Venus has always had the same atmosphere, and that's important because the temperature of the exosphere and the height of the exobase will be very different depending on what kind of atmosphere you have. If you just compare Venus to Earth, and that will affect escape rates, of course. Okay, so what about the possibilities of surface absorption? Now, in the beginning of the talk, I mentioned in the first scenario, the traditional view, that in the magma ocean steam atmosphere scenario, again, the hydrogen can escape to space and the oxygen can be absorbed by the surface. But we proposed something similar for Venus. And we proposed, as I've quoted here from our paper, that the large-scale resurfacing evident on Venus today, which took place over hundreds of million years, is a possible effective answer. And luckily, when you put out statements like this, sometimes people actually read your papers. And so Edwin Kite and Alexander Warren wrote this very nice paper in PNAS that examined this possibility. And the title is correct: a narrow range of early habitable Venus scenarios permitted by modeling of oxygen loss and radiogenic argon degassing. And this is a nice picture from there. I'm sorry, I should have blown up the picture on the right a bit more. This is from their LPSC talk. But basically looked at things like oxidation of the molten surface, which is what we're proposing, oxidation of the ash from volcanic outgassing, oxidation of the lava flows, and all of these sort of things. Are there ways to pull a lot of that oxygen out of the atmosphere that we cannot do through atmospheric escape? And they find there are some parameter spaces where this is possible. Not a lot of parameter spaces, but they do exist. And so this is kind of what the global picture looks like in a way. I want to go through just a little bit here again. So the idea again is you have this magma ocean period. Magma ocean lifetime is very unconstrained on these terrestrial worlds, somewhere between 1 and 100 million years, and that will depend how you evolve through time. The early accretion of planetesimals comes to an end. We have some kind of early plate tectonics or volatile cycling, where we go from a CO2-dominated atmosphere down to an N2-dominated atmosphere, as you can see down here. Our solar insolation is increasing through time. We have some kind of volcanic lip period, as I say here, these large igneous provinces, where large amounts of CO2 are released from the crust into the atmosphere, as happened during the End-Permian and the Deccan period. The CO2 increases creates a runaway greenhouse, your oceans evaporate, hydrogen escapes, and then there's another kind of period that happens after that. And sometimes people get these two confused, but they're distinct from each other. We have this resurfacing period. So if we look at Venus today, roughly 80% of the surface is relatively young. There are different estimates and fights in the community about how old this surface is. The traditional value was that the resurfacing period was fairly quick and happened about 750 million years ago. There are other people who say, no, that's way too long. It's more like 200 or 300 million years. I think that that's still up for debate when this happened. But regardless, roughly 80% of the surface of Venus is covered in relatively new, geologically speaking, basaltic flats. And that process is what would reabsorb the O2 from this atmosphere. Okay, but the habitable Venus scenario still requires water, amongst a host of other assumptions. But was there surface water on Venus? So what is the evidence for surface water on Venus? We talked about this a little bit before. I would say that there's evidence for water on Venus, but not so much evidence for surface liquid water, as I've already showed you. So I want to talk a little bit about this Pioneer Venus probe, because I did say I was going to talk about recent spacecraft missions. And on this probe was a probe called the Large Probe Neutral Mass Spectrometer. And in their published work from 1980, they published a D to H ratio for 150 times Earth's value. And as I said in my early slides, the H2O loss, when that happened and the timescale of that loss is completely unknown. But as we'll see, this value of 150 is not quite right. Okay, so what is and was Pioneer Venus? It was an incredibly ambitious mission. I have no idea how much this thing would cost today. It definitely would be a flagship type mission when you see what was involved here. First of all, it was 2 spacecraft. One was an orbiter, which you can see back here on the right with a technician in front of it, that included a radar, a magnetometer, a neutral and an ion mass spectrometer, and a few other things. It included a bus, literally a bus, that included a large probe. I mean, the bus itself included, a neutral and ion mass spectrometer. And it took data until 110 kilometers in the atmosphere before it released these probes that I'm going to talk about in a second. So the bus had its own mass spectrometers on it as it delivered the probes. And we had 3 small probes that included, each of the small probes had a nephelometer, a pressure, temperature, and accelerometer, and a radiometer. And it had a large probe that included a neutral mass spectrometer, which I'm going to talk about, a gas chromatograph, a nephelometer, pressure, temperature, and acceleration sensors. So here's the probe when it was launched back in 1978, and it arrived at Venus not too much later. The probe encountered Venus in December 78, and you can see that the probes were released into the atmosphere. This is what the probes release look like. Here's the orbiter. As I said, there were 2 spacecraft. Here's the bus dropping off its probes. Some went to the day side, a day probe. There was a sounder probe, a night probe, and then, of course, the large probe, the sounder probe, as they called it. I thought I'd show you a couple of cool pictures from the probe that were put out at that time. You know, NASA's always been pretty good at marketing. I think that this particular poster was put out by Hughes Spacecraft. Again, you can see the large probe here. Here's the large probe dropping off its probes into the Venus atmosphere. And here's a zoom in of this particular poster. So here we have a large probe descent. We have atmospheric deceleration from 150 to 70 kilometers when it starts to take data. Chute deploy and aerial shell jettison at 68 kilometers. The chute is jettisoned at 46 kilometers and an impact after 62 minutes. Just so you know, this is more or less the same kind of scenario that will happen for Da Vinci. They're really relying a lot on the legacy of Pioneer Venus, which was a highly successful probe. What does the probe look like? I'm not going to go through all this, of course. I'm just going to point out where the inlet port was for the large probe neutral mass spectrometer I'm going to talk a little bit about, and the gas chromatograph, which was on the other side of the probe. So both inlets on opposite sides of the probe, more or less. Here's some nice pictures of the assembly. This is the neutral mass spectrometer inlet, which has an explosive cap here. And here is a picture of the flight spare, which I visited at UT Dallas a couple times now on the left. And here's a picture that I got from the archives there of the thing opened up. It's not a very big, obviously it's about the size of 2 shoe boxes, more or less. It's quite small. Those are my fingers you saw there. And this is more or less what happened with the probe. We have the Pioneer multi-probe up here on the upper right. It releases the large probe. And December 9th, 1978 at 1845 UTC, it released itself. It starts collecting data and arrives a few minutes later. We have atmospheric gas collection in the upper atmosphere. We have a temporary clog of the inlets in the cloud layer, we think from sulfuric acid particles, and then a resumption of intake at less than 25 kilometers. Took a while for the inlets to become unclogged. So we collected 46 spectra as we flew down to the atmosphere, roughly one every 1 or so kilometers at altitudes from 64.2 to just above the surface at 0.2 kilometers. The ionization source was 70, 30, and 22 eV. The mass scale went from 1 to 208 AMU, but there were pre-selected mass positions, 232 of them. So they knew beforehand what they wanted to measure with fairly high mass resolution. Actually, mass resolution a bit higher than what Da Vinci will fly into its atmosphere, because it will use a legacy mass spec from Curiosity, a quadrupole mass spec. These are some papers that we have been writing on this probe in the past few years, led by my colleague at Cal Poly Pomona, Rakesh Moghul, where we have reanalyzed the data through the atmosphere for all of the different species. And that is work that is ongoing. We've had to basically relearn everything about this instrument because most of the people that worked on this probe have passed away or retired. And we discovered several uncharacterized trends. And this is one of the trends that was uncharacterized that we have been looking at. And this is the D/H ratio itself. So as I mentioned, in the Hoffman original paper, Donahue paper from 1980, they measured this 150 times standard mean ocean water, basically the D/H for Earth, 150 times Earth. But what we are seeing is that as we look at the profile for the D/H, the atmosphere, that it's quite high up here, at about 150 where Donahue and Hoffman made their measurements. Then it drops a bit in this region between 40 and 30, and then continues to drop as we get down to the surface. And that between roughly 15 kilometers into the surface, about 20 times standard mean ocean water. On the right is a plot showing some other values that have been measured over the year. As I mentioned, the Donahue, I said 1980, I'm sorry, I meant 1982 paper, where they measured, we're very close to their values because we've done a completely independent analysis. There's a measurement from de Berg. This is a ground-based measurement from 1991. We're not too far off from this de Berg value, certainly within the error bars. There have been other measurements in the higher atmosphere through different kinds of measurements, ground-based, some with this more recent paper from the WHO 2024 from the SWAR instrument on Venus Express, which has incredibly high values. So I would say the story for the D/H ratio is not completely set. But we believe it's probably more like to be 20 than it is these higher numbers, because there are ways to increase this D/H ratio as a function of altitude as you move higher up into the atmosphere. So that's just a taste of what we're doing. And I highly invite you to invite my colleague Rakesh Mogul to talk more about this really interesting data and all the interesting stuff we're doing with it as we find new ways to explore old data sets. Okay, I think I'm going to wrap up there. With the basic idea that Venus may have habitable conditions in its early history. Clearly, we need more in situ observations to confirm its geologic and volatile history, which we will get from these upcoming missions. We really need the ground truth for Da Vinci imaging with the IR imagers on Veritas and Envision, because Veritas and Envision missions not only have radar, but they have infrared imagers, and even Envision has a sounding radar that can peer into the subsurface realm of Venus to characterize any of these large igneous provinces that may exist or ancient aqueous features. And I should mention also that work by Jim Head and other people they believe, looking at the Magellan images, they have seen evidence for large igneous provinces, and Richard Ernst as well has been involved in some of that work. And finally, for this group, I just say the obvious, that exoplanets are definitely going to inform Venus's early history, and Earth and Venus will continue to inform exoplanets because they're the only, possibly habitable worlds we know about. So thank you very much for your time. I'll take any questions if you have any.
Thank you so much. So interesting. Gosh, thank you so much, Mike, for this talk. I'm sure that this particular group already has a lot of Venus fans, but I'm sure anyone on the fence has now been successfully converted.
Hopefully.
Hope. So yes, as mentioned, if there are any questions, we'd love to take them. If you want to maybe raise your hand using the Zoom feature to do so, or if you want to type in the chat. Anyone? Otherwise, I'll be rude and ask a question first.
Yeah, go ahead then.
Yeah, I think it's so great, and I mean, I think I don't know about others, but a lot of us are, more observers, and this like in situ kind of data is very unusual for exoplanet people, certainly to be considered. Kind of a technical question maybe, but what would you say is the kind of instrumentation that has come the furthest since the 70s and 80s? Because I mean, maybe some of them is kind of just we have these limitations and this is the best we can do, and maybe others have come a lot further. I don't know. What do you think?
Well, I mean, I think one thing, as I mentioned here a little bit, is that the radar imaging is going to be much better on Veritas and Envision. So Veritas is going to generate a global radar map that's going to be about 4 times, if I remember correctly, higher resolution than the Magellan maps. And then Envision is not really designed to be a global mission. In theory, it will take what we know about Magellan and Veritas and pick the more interesting region. It's going to have 3 different resolution modes. One is kind of a lower resolution mode, a medium resolution, and a really high resolution mode. And it will pick out the more interesting features on the surface to make those observations with. Another thing that they're bringing to the table, which is really interesting, is that they're going to have these infrared imagers on them as well. And the idea is to be able to do a better job of characterizing the kinds of rocks that we have on the surface. And there's been tremendous amounts of lab work being done, especially at DLR in Berlin, to look at these different kinds of minerals and things through the kind of imaging systems that are going to be on these missions, so we can characterize what we see on the surface.
Right.
Are these rocks really felsic? Are they granitic? What are they exactly?
Yeah.
And we'll be able to get that because we're going to have all this multi-band infrared imaging data from these orbiters as well.
Yeah. Incredible. Thank you so much. The next question we have someone from Anna Gulch.
Yes. Hi, Anna.
Your name wrong.
Yeah, that's correct. Hi, Mike. Thanks for the talk.
Hi. No problem.
About it. I wanted to touch base on what you consider specifically to be habitable. Do you mean, I guess it would mean sort of surface conditions that allow for liquid water. But is there a consensus across the community? Like you also have the exoplanet community and the geoscience community. Is that really sort of a term commonly understood by everyone, or do people still mean different things when they say habitable?
Yeah, that's a really good question. I don't think we've ever done a survey, Anna. I don't know. I mean, for me, it certainly means liquid water. I think that no one that I know of would argue that life on Earth could have moved forward without liquid water on the surface, right? There's still big fights about where the first life began, if it even began here on Earth. But certainly there's the shallow pool idea, which requires water. And of course, there's the idea that in the last universal common ancestor, there's evidence for extremophiles, which would be things that might have formed in deep ocean vents. And both of those scenarios, which are the two most prevalent ones and origins of life hypotheses, you need water. So I'd say we need liquid water somewhere for life to begin. I don't think anybody would argue about that, but it's a good question. I think at the next big conference, the exoplanet people they should do a survey in one of those big sessions and ask people, what do they think?
Yeah, maybe we'll do that at the next Rocky Worlds conference, which you should all be aware of, is coming up in January 2026. We have a question from Claire as well. Please go ahead.
Yeah, and thanks for the talk. I also like this idea of doing a survey of what people mean by habitability, because I agree with there's not, yeah, it'd be good to know what people actually agree on with this. But my question is about the need to get rid of all this O2 that would be left behind in the atmosphere. And from listening to your talk, it seems still like the only way to do this is to bring enough melt to the surface that can be oxidized. Yeah, I think that's what you were saying. So yep. I'm wondering if there's any capacity for these future missions to constrain if they find these large igneous provinces, to constrain the mineralogy well enough to be able to back this up, that they're like extremely oxidized or not.
I think it will be difficult. I don't know how well we'll be able to. I mean, it's not only just the surface, right? I mean, the surface could be oxidized. That's not so difficult. We're already in an oxidizing environment given the CO2 dominated atmosphere. So I don't think anybody would argue about that. The question is, how deep is it oxidized? So you need tens of kilometers of oxidation of the minerals on the surface to make the scenario work, depending on how much water was originally there. So you really need, I mean, more or less a drilling platform or some other way to get at the inside of the planet. Of course, if you could access to a recent lava flow, depending on where that magma comes from, yes, that could give you some constraints on the oxidation state of the outflowing magmas at that time. Would that tell us something? It depends, I would say. For example, what makes this so hard is that not all large igneous provinces of the same size have the same effect on Earth's environment. So a lot of large igneous provinces happen in the depths of the ocean, and the ocean has a great moderating influence on what comes out into the atmosphere. Also, it depends on what else it's erupting into. So if a large igneous province erupts into a carbonate strata, you can get a lot more CO2 released than if you don't. So a lot of it depends on what you erupt into to what you see. So we'd have to really know really well what the subsurface is in a lava flow on Venus to really know if it's giving us any information about what's going on. I think it's really challenging. But like I say, the first order, just knowing the oxidation of the surface is probably not sufficient to tell us if it happened or not, unfortunately.
Okay, thanks.
You're welcome.
I like the idea of a drilling platform on Venus. We can call the guys from Armageddon, right? They could do it. It's fine. Okay, we have
Yes.
3 questions on Zoom and then one after that on the chat. So the first person was Cedric, if you want to go ahead.
Hi everyone. Hi Mike. Very nice
Cedric.
talk. Thanks a lot. I had a couple of questions. The first, very interesting insight in D to H ratio you present there. Could you speculate on how to affect our picture of Venus? A lower D to H ratio would mean that comparatively we would have the need to lose less water, maybe?
That's exactly
But-
right, Cedric. If this lower
but-
D to H value is correct, that means we lose less water.
Mhm. But we don't know less compared to what? That's the point.
Yes, that's the problem.
Right.
I mean, as you know, I didn't bring it up, but I have in previous talks, and I think Cedric's heard me rant on about that. If you don't know what your primordial D to H is, you don't know what you've
Indeed.
lost with respect to. That is the big problem. We always do
Yeah.
everything in comparison to Earth because that's what we know the best, but that may not always be the right approach.
Yeah. Thank you. And second question was quite recently there was a paper published by Frank Celsis about the structure of the atmosphere in pure water vapor atmosphere, indicating that you might have lower surface pressure with surface temperature compared to the previous approaches with convective atmosphere. Meaning that the magma oceans could have been frozen much quicker than what was previously thought under some specific conditions. How does that interact with the scenarios that we know of these days?
Well,
it seems it could be important, but how exactly can it affect our picture of early Venus and maybe later Venus too?
Yeah. So there's been a more recent paper by Nichols and Lichtenberg, Pierre Humbert, and Bauer, which is quite good. They use another 1D model. I think Frank was using a 3D model, but they tried to look at this a bit to look for this convective instability in the lower layers of the atmosphere. And I think that they saw something similar could be possible. But I would just say, like I said toward the beginning, this is for a pure steam atmosphere. First of all, there are no pure steam atmosphere scenarios, as I showed you. They don't exist. Yeah. Secondly, how much steam, I mean, what percentage of H2O do you need to get this convective instability to work? Again, unconstrained. The parameter spaces are vast, so we need more work on this. As I said, very few people have looked at these things with 3D models, which are really important. As the Nichols paper states, without a 3D model, you don't know what's going on with the clouds. All of their work is cloud-free stuff. And as we've seen with habitable zone numbers and observations of exoplanetary atmospheres, if you don't include clouds, it's very difficult to really know what's going on, right? So that's kind of where we are, I'd say.
I see. Thank you very much.
No problem.
Thank you so much. The next person with the raised hand was Rob, if you want to go ahead.
Yeah, thanks for the talk. You talked a lot in the talk about the transition from the happy habitable Venus to the post-runaway state. But I'm curious as well about the initial state going from the magma ocean to the happy habitable state. Specifically, there's a paper released by Turbot in 2023, looked at the question of not just sustaining liquid water on the surface, but also condensing the liquid water into oceans in the first place. And they were showing there that if you can consider the water condensation problem, the inner edge of the habitable zone moves much further back. And in that context, Venus could never have condensed liquid water into oceans. So I'm wondering where those results fit into this picture.
Right. So I think I talked about that in the early part of my talk. The paper is not from 2023. You're talking about a 2021 paper, I think. But
no, there's a paper in 2023, I'm pretty sure.
2023. Okay. Well, anyway, I mean, I think it's the same simulations, if I remember correctly. But again, a lot of this depends upon what kind of atmosphere you're modeling. And the 3D simulations that they have run are extremely computationally expensive. And there are a number of shortcuts that are involved too. So in their simulations, they never actually model a proper magma ocean atmosphere. If you look at those results from Bauer and the Nichols paper and such, we're talking about atmospheres that are hundreds of bars in terms of pressure. In the Turbay paper, most of their simulations are 10 bars, or I think they did a couple experiments at 30 just to see where things were going. Also, they only model a couple of atmospheres, like I said, more traditional steam, CO2 or steam N2 atmospheres. And again, the parameter space is much vaster than that. So I would say within what they have attempted to do, which is amazing and the best work that's been done to date, we just don't have enough information. So I can't say whether they're right or wrong. They could be right, but we need to do a lot more modeling to understand if these other kinds of atmospheres show the same sorts of shortcomings or not for this early hypothesis to get things to rain out in the early atmosphere. If it even did that, again, that's just the current kind of hypothesis about how the first oceans started that comes from the earth science community, that you had the steam atmosphere, it cools down, the water condenses out on the surface, and you have oceans very early on because there's evidence for oceans already in the late Hadean. So I think that's what we're stuck with. We just haven't sampled enough of the parameter space at the moment, in my opinion.
Thank you so much. We are just hitting the hour, so maybe we can have one final very quick question from Oliver. If you want to please go ahead.
Yeah, thanks. I mean, you emphasize the water solubility pushes water into the interior of the planet. A student I work with, Teresa Constantino, published a paper last year arguing that there isn't evidence for that water still in the composition of Venus's volcanic gases. So I wondered if you could maybe comment on that link between what the interior should be and its climate history, and then whether, you know, ongoing volcanism evidences one way or the other Venus's past climate state.
Yeah, I mean, if I remember correct, I think I remember this paper. One thing I didn't understand about that paper was that there was no citation to the Gallier and Skyar work, which explicitly states that in a high pressure atmosphere for Venus, you won't get H2O outgassing from volcanism. And so, I mean, if Gaillard and Scalé are correct, then you get exactly what you expect, very little water outgassing. If they, you know, if she has a better explanation for why you get water in a high pressure atmosphere out, I'd love to hear it. But I didn't see any evidence for that in the paper, as far as I recall.
Great, we should follow up then.
Definitely.
Thank you so much. And apologies as we don't have time to get to all the questions that are in the chat. So a huge thank you to Mike and a huge thank you to everyone asking questions. If people want to have the keep the conversation going, don't forget that there is actually a Discord channel space that you can join if you want to do that. And I would also like to remind you of our next talk, which is coming up on the 6th of March. We will have Catherine Leclerc. And if you want to hear more about volcanism in the solar system, Catherine will be telling us about tidally driven volcanism and mass loss at Jupiter's moon Io. And this is the talk that was unfortunately rescheduled due to the wildfires that were going on at the time. in January on the US West Coast. So please join us for that. And remember that if you enjoyed this talk, or you want to watch it again, or you know someone who was sad to have missed it, or if you have some students interested in Venus, there is a YouTube link. There's the live stream will be available on our YouTube channel afterwards. So huge thank you again, and see you all next month, everyone.